Hello everyone. I hope that you are all doing well and staying safe. First, I would like to apologize for the delay that occurred due to unforeseen reasons. Hoping that you will enjoy the last session of the Python course, which is part of the Virtual Software Internship organized by SPE University of Boumerdaz student chapter. My name is Nabila Widat, a Master Petroleum Engineering student at the University of Boumerdaz in Algeria, and I will be your moderator for today's webinar. Today's session will be delivered by Mr. Divyanshuc Vyas. Mr. Vyas holds a master's degree in petroleum engineering from IIT ISM Dambad, currently working as a data science analyst at Accenture AI and the CEO of Petroleum from Scratch with over more than 1 year of experience with oil and gas applications and problem solving using Python. He worked on numerous full-scale to mini-scale projects, ranging from core reservoir engineering concepts through drilling engineering concepts to oil production engineering and numerical simulations using Python and its packages. Mr. Vyas actively maintains a GitHub repository for oil and gas data analysis and machine learning and deep learning to help and mentor the community with whatever he learns. So before we start, I would like to remind you to keep your microphones muted and to type your questions in the chat box. Mr. Vyas, the mic is yours.
Thanks a lot. So it's great to be back. I had health issues back in days. I actually contracted COVID, and that's why we had to stop. I could not deliver the lectures. And then as I got better, the timelines crashed with, I guess, the university exams and all. So a lot of things happening at the same time. So we immediately have to be around. But it's great to be back on track for a very interesting session. I know we are combining two sessions in one, but by no means I am ending my availability here. If in case any of you want to start from scratch or any of you want to discuss or maybe teach me something, I'm always available. So, so this session I'll be talking about machine learning from scratch. I'll talk about what machine learning is, and then we will look at a few projects to develop an understanding of how machine learning works. Then we will understand what is the hype about, right? Why people are, favoring machine learning so much these days. What's good in it? How does it work? We'll look at a couple of algorithms in machine learning. And then, if time permits, we'll also look at deep learning, which is nothing but a different algorithm, but it trains on data using a machine. So it's eventually a subset of machine learning. So by the end of the session, I aim to, develop a mindset. In case you have no idea, but after the session, you will have an idea that machine learning is some interesting concept and it can be used to solve problems. And it's not a ghost, or it's not that tough to be worried about, right? So yeah, so let's start. I'll just share, and I'll talk a lot in this session because we have 1 hour to talk about. I won't be spending time in trying to code things up in front of you, because that can be done. There are a lot of resources, but as an oil and gas and petroleum engineer, how to think about machine learning, that's the main theme of this session, right? So I'll share my screen. Let me know when you can see my screen.
Yes, sir, it's visible.
Okay. Okay. So I have a few projects open in my web browser. So I'll talk about a few. So basically, why machine learning is so popular and what is it is the first topic that comes to mind. Whatever tools we have learned, Python, for example, NumPy, Pandas, data analysis, data visualization, all we do just to get to this point where we can develop a model, right? What is the difference between a data analyst and a data scientist? The difference is here, right? If you are a data analyst, you are analyzing data, you are saying, and you have a huge data set. Everyone has a huge data set. But what makes a data scientist? It's not the analysis of the data. Yes, it is important. A data analyst would take that data, maybe do a Power BI visualization, do a dashboard analysis, do a Python visualization, do various sorts of reporting from that data. Maybe say that this is the property about porosity column in the data. This is the property about this column in the data. There will be a lot of informations that he might be able to provide. But can he or she provide a model that you can use to provide future insights, to provide information about the unseen data, to provide, input output kind of thing? That's what a data scientist can do. And what data scientist uses, he uses a bunch of algorithms called machine learning algorithms. The name machine learning comes from the fact that you take data, you feed data into a machine, the machine understands various properties from that data, and it becomes a smart version of itself. That smart version is called a model. You use that model, you put in new information into that model, and the machine speaks out outputs from that information. And those outputs are very valuable in terms of making decisions, right? So you must have seen terms like decision scientists, people scientists, and various things. They are all using one model or the other. Now, why machine learning is being so popular these days? Because traditional techniques were based on human experiences, right? In a way, machine learning has always been there. So if you are in a part of a team, what do? Whenever you want to get expert advice, you go to the senior most person and you ask him or her that, sir, can you please tell me what should I do in this condition? Exactly what machine learning can also provide help on, right? The reason you go to the senior most person is because that senior most person has had a lot of evidences in the past of the same particular problem. He has seen a lot of data, in short. He or she has worked on a lot of, why they are called experiences, because they have seen a lot of things in their life. What if we could capture all of those things in terms of data, take them into a spreadsheet, feed it into a machine, train the machine like that or that particular individual was trained, and use the machine rather than that individual? Now, machine can perform better, right? Because machines don't forget, right? But there are loopholes about humans. So that's why machine learning is so popular. And I tried this when as soon as I understood this thing about machine learning, I tried to verify this thing. And this is a project that you see in front of my screen. That's a project that I did not, it's not a practical project that you can apply and provide help in the industry, but it's a verification of machine learning. Machine understands physics, in short, right? And given that you have a huge data set to feed to the machine, right? That's the loophole that people talk about in terms of machine learning, right? If you don't have huge data set, then machine learning might not be that useful. If you have a huge data set, then machine learning can be very useful. That's obvious, right? That's why you go to the experienced person and not to the less experienced person, right? So let's see what I'm doing right now in this particular project. So a lot of things are commented out, but that's not the aim right here. Coding, I guess I am sure you all can do, because it's been 2 months since the introduction of this thing. Everyone knows a bit of it. About machine learning. So in this project, what I'm trying to do is, there is a popular correlation in reservoir engineering called the Timur's correlation. What Timur's correlation does is it calculates permeability based on porosity and connate water saturation. And this is the formula. So basically, this is the physics that the particular reservoir follows. You can imagine, right? Now, traditional approaches, you have porosity value, you have saturation value, and you take those values and you calculate permeability because you know this entire formula, right? Now, if I ask you, what about the applicability of this formula throughout the globe? Can you be sure that this formula, which is more like an empirical correlation, can you be sure that this particular correlation will be applied across the globe? Are you sure about that? Are you sure that this will perform greatly like it has been performing in North Sea, for example? Can it perform equally better in, let's say, Barmer in India? Can it do that? I don't think so. I even if I, I would tell that to myself, I have no evidence to believe that, right? Now, what if I had the data from porosity, I had the data from connate water saturation, and I had, let's say, 70,000 to 80,000 samples of porosity and connate water saturation. I can build a correlation from that data myself, right? I can feed that data into the machine, make the machine understand that particular phenomena, use a particular algorithm fitting to my case, and develop a porosity permeability correlation myself. The benefit of that process is that that correlation is in fact developed on that particular field and can perform very well on that particular field. Now, with that understanding, when you go to a next field, you train the machine on the next field's data. If using machine learning again, machine performs equally well on that field. So this is a robust algorithm, right? You're not using the same old correlation across the domain. You are being very, very practical in your approach. So that's why if you have data, machine learning can help a lot, right? So let's see. So what I've done is basically very smartly, I've just created random samples of this data. So this is a data that I have created. You can try this as well. So I have created 70,000 rows of porosity and 70,000 rows of connate water saturation. I've thought about it, the values and all. I discussed with my seniors about these values. And then I created these random number arrays. And then I calculated permeability from that as well, this formula. Okay, I have used Timur's correlation to calculate permeability from porosity and connate water saturation. Now you would say you already have the answer. Yes, I do. But the main aim here is to check whether machine can learn this formula. All we will provide to the machine now is 3 columns of information. We will provide the machine with porosity, we will provide the machine with connate water saturation, and we will provide it permeability. And we will just sit and observe whether machine can understand the Timur's correlation as well. On the back of my mind, and every one of you, you guys know that this permeability calculation has been obtained from the Timur's correlation, but we will, at the end of this analysis, verify the same calculation by a machine. Okay, let's see how we did that. So I have created a data set. Okay, everyone knows how to create a data set. So I've used the shortcut. I've created a dictionary and then put it into pd.data frame. I guess I have discussed this thing. And then these are the 3 columns that I have. So in machine learning, what we do, we always take X and Y. What is X? X is all the set of columns that are used as inputs, and Y is the column that is used as output. Now, Y can be continuous variable, for example, permeability, height, oil production rates, anything which is a numerical, physical quantity which can be measured on a scale. It's basically, it's basically a continuous variable. And for calculating continuous variables, you use regression, or you use prediction, or you use artificial neural networks for predicting continuous variables. But this particular task is called regression, right? But if you have something like a yes or no, true or false as your output, that task is called classification. So these are 2 legs of machine learning. One is regression, other is classification. There is also a 3rd leg of machine learning, which is forecasting, right? That takes about the things that deals with the models that train on historical data and forecast future data, right? So that's not what we are trying to discuss today. It's a very practical thing which deals with regression for now. Okay, so we have 2 columns. So porosity and connate water saturation, they are the input vectors, right? We call them the feature metrics. Whatever is an input is called a feature, right? A single input column is called a feature, and the output column is called the target. Okay, so porosity and connate water saturation are the 2 feature columns, and permeability is the output column. All right. Then this part of our analysis is called exploratory data analysis. It's called EDA. What we try to do in EDA. So this is a very simple problem. So we don't really need EDA, but in complex problems, you will have problems like missing data. You will have problems like, outliers. You will have problems like noise in your data. A lot of problems, different data sets have different problems. The first step to identify and diagnose those problems in your data set is to visualize things, right? For example, if I want to visualize whether or not my data has missing values in it, I would do a heat map, right? I would do a heat map of that data set, entire data set, and check where my null values are. And whatever column shows me a majority of null values, I have to target that column first, right? So that's how we address one problem, and then we address the next problem. So visualizations are very important. Now, this visualization is just the visualization of the two columns I have. So porosity is one column and saturation is another column. All I've done is I've done a distribution, which is called a KD plot. And I'm looking at a normal distribution for both of them. Now, ideally, it is believed that if your features are normally distributed, that's a great data set, right? Why that is so is because these data sets, when you feed into the machine summarizes them into 2-3 parameters, and the entire data set can be summarized into standard deviation and mean. So that's advanced statistics. But if you are starting up, all you need to know right now is visualizing data tells you a lot of information about data, right? And that's called exploratory data analysis. So what this data set tells me is, this visualization tells me is, the Conet water saturation column, it's distributed like this thing, this orange vertical distribution. The average Conet water saturation of this entire reservoir is 10%. And there are no outliers, because if there was an outlier, you would see spikes of orange at 0.3 as well, 0.5 as well, but there are no outliers. It is a perfect normal distribution. Porosity, the average porosity is 0.25, you can see from this graph, and there are no outliers of porosity as well. The range of Conet water is from 0.01 up to 0.15, I guess. For porosity, it's from 0.1 to 0.5 or something like that, right? So you can already guess what kind of reservoir it is. It might be a sandstone, right? So these are the informations that you get after visualization, but you cannot predict things after visualization. So we move on to machine learning next, right? Okay, then to do machine learning and to validate whether your machine has done well, you have to do a very important step. You have to keep a part of your data set untouched, right? That's a step called train test split. So basically, first you have to separate, like I told you, input matrix and the output matrix, you have to separate them like this. Then what you have to do is you have to, let's say 20% of the data, randomly sample that out and keep that aside as your validation data set. Don't touch it. Keep it like the foreign data set that the user will input, that the machine has never seen. Take 80% of the data set to train the machine on, right? It's very intuitive. Train the machine on. Now, how we will train the machine on? In some data sets, you will need to normalize the entire data to a common range between 0 to 1, because that helps you train better models, that helps you convert the entire data into a homogeneous range, right? And it trains the data faster, right? So that being said, so the next step that we do, you can see I've commented this out because this is an old code. So I'm not sure what I did there, but you have seen that X train, X test, Y train, Y test. So basically one line of code, and you have split the data set into two halves. Okay, not two halves, but 70-80, 70-30 or 80-20 kind of thing. Now, what you will be using to train the data on is X train and Y train. Okay. So ultimately, what you are trying to do is you have X train, you have Y train put in front of each other. There is a mapping between both of them, right? X and Y. The machine will train on 70,000. I guess we are using 20% as test set. So 80% of 70,000, that is 56,000 rows it will be using as a training set. And it's more than enough evidence, right? If you ask a human, can you remember 56,000 instances? The human would say, I don't know. But the machine will remember. Machine will understand, right? So 56,000 X's and 56,000 Y's, you put them in front of each other. The machine trains on it. Machine understands the relationship between X and Y, and then it finalizes that relationship. Okay. Finally, once you have trained the machine, so I'll show you. So basically, there are various possibilities to do that. That's an important decision in your data science project. What algorithm should you train on? Now, you already know this is a regression problem. So you have to use one of the regression algorithms. You cannot use a classifier. You cannot use, decision tree classifier, a random forest classifier, or logistic regression. Logistic regression, mind you guys, that's a classification algorithm. That's not a regression algorithm. It's it's called regression, but it's a classification, binary or multi-class classification. Here you can use, because you have a good amount of data, 70,000, you can call it a good amount of data, but that's not too good. If you have millions of rows, you can use artificial neural networks, right? That's called deep learning, right? That's a different part of this project. So you can try around various algorithms as you develop your understanding, but that's not the main goal here. Once you have, let's say you have trained a regression model on the data set, here I've gone ahead with decision tree regressor, right? You have seen that I have also tried artificial neural networks, but maybe it did not perform that well. It had problems in understanding the relationship. But finally, I went ahead and trained a decision tree regressor. The way you train a decision tree, any machine learning model, first you have to import from a library called sklearn. It's called scikit-learn. You import the particular model. So in using this particular regression, if you want to import, let's say, linear regression, so you would have to type something like this from sklearn dot linear models import linear. So you can press tab and it auto completes. But right now I've not run this notebook, so it's okay. So linear regression, okay, linear regressor. So all you have to do is import whatever model you want to build on. So suppose you have imported it, then you have to initialize that. You have to tell the code that, okay, I'll be using this particular model. So this particular step is called initializing. Okay. So model equals to decision tree regressor, and whatever you pass in this brackets, they are basically the properties of these model that you are going to use. If you want to use fancy language, you call them the hyperparameters. All right. So once you use this model, then you fit it, right? This step is called training. Okay, so model.fit x train comma y train. All right. Then once you fit the model, then you are ready to say that your model. Now you have to observe that you are fitting the model on x train and y train. You are not using x test and y test at all. You don't even use it in your analysis. You don't even use it to calculate anything. You just keep it aside. Okay. So once you have fit the model into this thing, then you predict, right? So this is how you predict. So you pass a bit of information into this model.predict, and that model takes that information, and based on its understanding, it predicts y values. Okay, what's y here? Y is permeability, right? Now, once you have done the training and everything, now you have to check whether your model performed well or not. There are two ways to do that. One way is using visualizations. Like you can compare your model predictions against your actual data. And if that data lies on y equals to x line, that is 45 degrees slope, then you can say that that's a great performance. But if your data just goes beyond 45 degrees line, that means your model predictions are not concurrent with the actual data, right? The other way, which is more like a quantified way of doing it, is doing what is called a mean absolute or mean squared error, right? You can calculate the error between the mean error between the actual y and the predicted y, and then you can use that error, and then that error tells you whether your model performed well or not. Basically, that error has to be checked with the data range. For example, my average permeability in the entire reservoir was 2000 millidarcies, and my mean squared error in predictions is, let's say, 2 millidarcies, then that's a great performance. Or let's say 20 millidarcies, also fine performance. But if your error was around 1500 millidarcies, then that's a terrible performance, right? So what I've done in this case, first thing, I have also checked that during the training, my error minimization is happening or not. Yes, it is happening. And then I have done that visualization. I'll just show you the y equals to x line. So you can see on the y-axis, I have the actual k values. On the x-axis, I have the predicted k values. You can swap them around. You can see it's lying very close. Some cases it's not performing well, but more often than not, 99% cases it's doing well, right? That tells you that the machine has understood the correlation, because whatever the Timur's correlation was providing you, the machine is also able to understand that and provide, right? And finally, I have also done mean squared error. You can see percentage mean squared error is very less, even less than 1. That's not always the case because this is a randomly synthetically created data. That's why you are seeing that greater performance. But normally, you have to be case specific. You have to check your data and then comment on whether your performance was good or not, right? So this is how, you can train the machine and say that machine and verify that the machine can understand the physics given a lot of data is there, right? So that's first part of our today's session. Before moving on, we will take 5 minutes to discuss any doubts if there are there or anything that anyone wants to ask. Then I will talk about the other projects for today. So is there any doubt we have? I don't see any doubts. Okay. If you have any doubts, you can type them into the chat. Just a second. Yeah, so let's move on. We will.
Sorry, I think we will let the Q&A session for the end of the session.
Okay, sure. Okay, yeah. So with that understanding, now we will move on to, I guess, I have a project with me. Just a second. So I'll give you a brief heads up about a machine learning algorithm called linear regression. So this is a project which will give you a brief idea about various sections of a machine learning project, right? Various sections as in what is the exploratory data analysis, how do we do various things, how do we look at descriptive statistics of data, how do we do that all in Python. So this is a well-documented code from GitHub I have pulled up. So let's see what is there in it. It's not an oil and gas example, so I'll just quickly run through it, but it will give you a brief of what you can do with data and how you can solve various problems in understanding the data, right? So yeah. So linear regression in Python, the way linear regression works is basically you have, it takes what, basically it calculates a particular prediction of Y. It takes data, it calculates Y from the data. So linear regression is basically Y equals to mx plus c kind of thing. And then M and C are firstly randomly calculated, but they are wrong, right? So you have to correct the values of M and C based on the data. So it iterates over the data one by one, updates the value of M and C, calculates Y, compares this Y with actual Y, calculates the error between both of them. If the error is huge, it updates the M and C again, tries to calculate Y predicted and compares it with Y actual. If the error is still huge, it again updates it. Keep on iterating like this, keep on updating based on the error between predicted and the actual Y. And finally, once the M and C, the predictions are very close to the actual values, the M and C can be considered to be actual representation of the physics of the particular model, right? Or actual M and C in short, right? So that's where machine learning models stops training. That's called a successful, right? So basically it keeps on iterating over the data, keeps on improving its parameters. M and C are called parameters of the model that the model calculates after fitting on the data. And it keeps on training. And finally, once the parameters satisfy the actual Y, that's when the training stops. And that's when this particular model, we compare it with, the actual data like I did in the Y equals to X line. It lies close to Y equals to X line. Then we trust this model, and then we go to the foreign world, and then we create apps on based of this, and then the entire world can use this model to make predictions out of it, right? So this is how machine learning goes on, right? Okay, so linear regression. So data we are using is basically, I guess, the house price prediction data. So there are a lot of columns in this data. There is the average income of people in that locality. There is the average area of a house. There are average number of rooms, number of bedrooms, population, price, and address. So address won't be useful, but price is the output column in this case, and a lot of other columns are there. which will be used to train a machine learning regression model, right? So this is more like a multiple linear regression problem. Okay. So first step, like we always do, we have to check out the data. Okay. So this is df.head. You print the first 5 rows of the data just to look at how various columns look like. df.info gives you how many non-null values are there. You can see, and what is the data type of each of these columns. Because the machine cannot take string data set. Machine cannot take machine only trains on numerical data set. That's why float, you have to ensure it's either a string. No, it's either an integer or a float. You can see it's an object, address is an object, so we won't use the address column. For simple projects, we don't, but if it captures a very important information, we convert it into a dummy variable, which is more like a numerical version of the string column, right? Okay, so we have checked out that there are no null values in this data set, and maybe address column has to be neglected. Okay, then we move ahead and we look at the various descriptive statistics of the data set, right? So this is just a simple describe. See, it gives you a lot of information. It gives you the count of the number of values in a column. It gives you the average value of the column. It gives you standard deviation, the minimum, the percentiles, and the maximum. So in short, using this, you can get a lot of information about what statistical properties the data has, right? So you can see that the average income of this entire community, the entire city, I guess it's a city or a state, the average income of all the people was around 68,583. And the median income was around 68,804. So it's more or less equal, almost there, right? So it's not that median income is too huge or too less. So there are, I guess, no real outliers maybe. Okay. So average area, house area, you can find out average number of rooms. So you can see the mean average. So the 7 is the average number of rooms in this locality. So it's not necessarily a slum area or something. There are 7 rooms at an average in each house, right? So that's something. That's a great like size of a house. Right? And average number of bedrooms, 4 bedrooms. Wow, at an average 4 bedrooms. So you have a picture of your what kind of locality this is in your head. So that's the usefulness of this particular step. Then you do the EDA. There's a very useful thing called pair plot that tells you how various columns are stacked in front of each other. So you can see it basically creates a matrix of plots. You can see average area income versus this particular plot I'm talking about. It's a circle, basically a nothing plot, right? So you can see average area income and average house age. They are not related to each other at all, right? This plot looks like it shows a linear correlation. So you can see average area income is very nicely related to the price, right? So these are the information you get from a pair plot at one glance, very descriptive, but it takes a lot of time to display this pair plot, right? And this is a plot that I showed you. It again tells you about the, the distribution of the data set. This is a heat map that tells you that what column is correlated to what, right? This is a matrix that tells you a correlation information amongst the columns, right? So let's observe this. So 0 point, so darker the column is, higher the correlation. So let's see. Of course, the middle ones are stacked in front of themselves. So it is one correlation, but average area, house age is not at all correlated to the income of people. Area population is nicely correlated to price. Average bedrooms are nicely correlated. So this particular thing is darker. So you can see average house area is nicely related to price. So stuff like that you get to know from this, this particular step. Okay. Next up, now we are ready. Now, so basically this correlation thing and all, why do we do that is because some columns, they are not at all correlated with the output variable. Okay. And those columns can act as noise for the model. These columns are not important. Why would you ask as an input some information which does not contribute to the output? That information is rubbish. That's garbage. You don't need it. So you have to ensure that whatever model you are creating, whatever data you are feeding into a model, only takes in useful information. It does not take in rubbish. It does not take in irrelevant information. So you do the df.correlation and you find out what are the columns which are nicely correlated with the output column, and then you pick those into your model. The ones that are not like that show 0.0003 correlation, they are not important for this model. You can drop this, right? Because we are talking about linear regression right now. So they are not linearly related, so you can drop them. Right? One more assumption of linear regression is that the columns must not be interrelated between, like, among each others. So if I'm taking X, all of the columns of X must be independent and they must not be interdependent. So there must not be multicollinearity, right? So that's a mathematical, concept that linear regression is based on, right? So if they are basically interrelated amongst themselves, the linear regression model does not perform. So this plotting can be used to do that as well. We can eliminate or combine the features that are interrelated, right? Okay, moving on. Now we are ready to do what we have already seen. So you take in X, you can see X has area, house age, number of rooms, bedrooms, area population. As expected, we have dropped the address column, and Y, which is the output, is basically the price part. Okay. Then we do a train test split. In this data set, we are using 40% of the data as unseen validation data, right? And 60% as the training data. Okay. Now we have imported linear regression. Okay. And then we have trained the linear regression model, X train, Y. Okay. And finally, when we have trained the linear regression model, a very interesting part, because it's a linear model always has intercepts. It always has slopes, coefficients. Okay. So if we imagine this model to be of the type y equals to m1x1 plus m2x2 plus m3x3 plus intercept, where x1, x2, x3 are all of the features, right? So we might want to know what are m1, what are m2, what are m3 and all, right? So this is the way to find them out. So for this model, the intercept is this. If you want to find out what is the coefficient of all the other columns, this is the way to find them out. Okay. lm dot coefficient underscore. So whatever is followed by an underscore is a parameter that is found out by fitting the model, right? Okay. So we have all the information and we know the information from the model. Now we can use this information to predict the price of a house. Okay. And this is the step to do it. Again, we have done the same thing. We have calculated the predictions and we have plotted them against the actual house prices. And you can see it's very, very close to the y equals to x line. But as we deal with practical and real world data sets, we can see more and more noise. In the synthetic data, the one that I showed you in the porosity permeability thing, everything was on the y equals to x line, but not every case is similar. You can see a lot of noise, but it's good. It's good. In real world cases, this is a great performance. Okay. And then finally, we do the model evaluation. Okay. Model evaluation is nothing but a mean squared error and stuff. And that's it. So basically, this is the skeleton or the structure that a machine learning model follows. Okay. So I'm pretty certain that this understanding is great enough to go to a very interesting petroleum related project. So we are going to use regression to train a production forecasting project, right? We are going to use wall field data set. It's not forecasting. It's not correct to call it a forecasting project. It's more like a predictive oil, or whatever you want to call it. We are trying to predict oil rates based on other parameters from the well level. Okay. All right. So if you want to access this data set, this is the link. Okay. The GitHub link, as always, I'll share this with you. Okay. Okay. So we have this data set. So if you look at the various columns in this data set, we have on-stream injection hours, we have bore water volume, we have on-stream production hours, we have average downhole pressure, we have average temperature, average delta P of the tubing, average choke size, average wellhead pressure, average wellhead temperature, bore oil volume, bore gas volume, bore water volume. So basically, we want to forecast oil rates. We want to predict oil rates. based on all the other parameters that you just saw. This kind of data set is called the time series data set, because you can see the index is not 0, 1, 2, 3. The index is like dates. In these kinds of models, sequence is more important. If you ever do a forecasting project, you will not do a randomized train test split. You will always do a sequential split, right? You have to keep a sequence in place. You never want to change the sequence, right? For example, decline curve analysis. If you place the initial data somewhere at the end, that's basically terrible. That's wrong. So the reason that the decline looks like the way it looks like is because of the sequence that it follows. A decline is always, a time series data. Decline curve analysis is always on the x-axis. There's always time, right? So that's why these kind of data sets are called time series data sets. Sequence is very important. On the x-axis, you will always have date time, right? So this is how there are two additional informations you want to provide in a date time data set, which is this: index column equals to 0 and parse dates equals to true, which is basically a way to say that convert the dates into date time objects rather than string format. Okay, I might sound advanced to a few, but as you go on practicing, you will understand these things are very simple. Okay, so these are the columns that we have. You will realize that the entire skeleton is the same that I have always followed in the machine learning project. Okay, so we are looking at the columns. Then you do a correlation analysis as a quick hack to eliminate the irrelevant columns. All right. So this is the heat map that you just saw, right? So this heat map tells us a lot. If you spend 10 minutes on it, which we don't have right now, if you spend 10 minutes on it looking at this heat map, you'll find out that some columns you have to eliminate, some columns you have to keep, or some columns you have to combine, right? So depending on how advanced you want to make a project, how much time you have, you can do various things with this data. Okay. So you can see from this above metrics that some features are fairly interrelated, which breaks the assumption of linear regression that I just told you about. And hence we will see troubles in a model performance. Failure is also a learning. So we will fail in this model, and I'm sure that we will fail in this model, but that will teach us. So I just told you that interrelation between features is a terrible thing for a linear model. But how do you prove that? Let's see, how can we prove that? Okay. So this is, I'm plotting the correlation of each of the features with the output feature. I'm ignoring the fact that they are also interrelated. I'm assuming they are independent. I'm just going ahead as blind, and I'm ignoring the faults in this model. I'm just going ahead and taking all the features, plotting the correlations of them with the output feature. And you can see that this is gas volume is almost 99% correlated with oil rates. So you have to take that out. And why is this happening? Because if you know oil rates, if you know gas rates, if you know water rates, basically two of them can lead to third, right? So you don't need to know all of them three. You can eliminate one of them. Okay. So that's why you can eliminate gas volume, because it's like a duplicate feature. Then you can also eliminate this column. What is it? Average choke size in percentage. So you can eliminate this particular guy. So depending on what's your significance level, I guess if I keep 0.2 as the significance level, I can ignore each and every feature which is less than 0.2, either negative or positive, right? So basically 3 features I can ignore, and the fourth one being the gas rates. Okay. So once I ignore all of these columns, I have a data set that I believe is more important to my model. Okay. So these are the magnitudes. You can see this particular has very less correlation, and 0.18 is also less. So you can eject them all. Then finally, we have picked up the input columns. Okay. So the condition I put is, if your correlation absolute magnitude is greater than 0.2, you keep that. If it's greater than 0.90, you remove that. Okay. So that's how I have selected the relevant columns. Once I have selected, then I will name X and Y the way that we always do. And then we do the train test split. You will observe that it's not the same way as we have done in the 2 other projects. You can see I have done a sequential splitting because it's a time series data. So what I'm doing is basically 3000 days ka data I'm taking as, input, training data, and the following section of the data I'm keeping it as a validation data. what sklearn train test split does is basically it shuffles the data and picks randomly some part as training and some part as testing. But we cannot do that here. But yes, of course, there's a utility, there's a parameter in that train test split sklearn function that we can provide that don't do a randomized splitting, don't do shuffling, keep it sequential that you can use, but to keep it simple and doing it this way. Okay. So I'm using basically last 291 days, which is almost 1 year data, and keeping it as a unseen validation data. And the other 3000 days data, I'm taking it as a training data. Now, like I told you, some cases will require, scaling the data. Why? Because suppose your one column has a magnitude of thousands and millions, and one column is in 0.1, 0.2. Then if you give it to a machine learning model, it will assume that the columns having higher magnitudes have higher importance, which is not always the case, right? What if the 0.1, 0.2, they are actually more important informations? So to deal with this kind of problem, what we do is we bring each of these columns into a 0 to 1 range by what is called a min-max scaler. So this is called feature processing of data, feature scaling of data. So this is an important part of data processing, right? So I have done, because I'm using a linear regression model, I know that linear regression depends on the scales of the data set. So I have to do a scale, right? Even if you use artificial neural networks in deep learning, even if you use distance-based models like k nearest neighbors and stuff, wherever magnitudes play a role, you always have to make sure you do scaling. Where magnitudes don't play a role, for example, in random forest, in decision tree, they are based on if-else kind of splitting of the data. In that case, you don't have to do the scaling. But right now I have to. Okay, so I have scaled the data and converted into a train scale and test scale. Okay, the syntax is very simple. Okay, then I have trained a linear regression model on X train scaled comma Y. So basically, we are trying to figure out the mapping between scaled X and actual Y. Okay, because we can do that. We don't have to scale Y part, right? Because that's a single column. That's not a set of columns. So if you are looking at a set of columns at once, there must not be any bias between either of them, right? So we do the scaling and we train the data like this on X scale comma Y, and then we do a prediction, right? Okay, so this is the training performance of the model. Now you can see that in some cases, the blue part is the model, it's the blue part is the prediction, the orange is the actual data. In some cases, you can see that the predictions are falling into negative, very, very like minus 2000 oil rates, they are saying. So is that good? It's terrible, right? A lot of cases, you can see the predictions are falling into negative territory. Now, we go back to the assumption that we are breaking. We go back to the top. We talked about this thing, right? So I told you that we will fail, and we have failed. Okay. So we always have to make sure we keep in mind the various, Google it up. Google what are the assumptions of linear regression model, and make sure you follow those assumptions whenever you are building a linear regression model. Okay. So finally, we are sure that this way linear regression won't work. Okay. So what if we train other model? Let's train a random forest regressor model. So the way to do that is first we import a random forest regressor. Of course, we can also deal with the assumptions of linear regression to make it better. But I wanted to show other models as well. So I have random forest regressor. So again, you can see now I'm not taking the scaled version of the data. Now I'm taking the normal version. The same skeleton. First, I have imported the model, initialized the model, fit it on training data, predicted on testing data, and then I plotted things up. And you can see everything is beyond like greater than 0, and everything is close to the actual data. You can see on the unseen data, the right side of this red line, the actual data is the green line, and the predicted data is the black line, which is not perfect, but it is very good. So basically, the model has understood the historical data, which is in oil and gas terms called history matching. Of course, it's not time series right now, so it's not perfect history matching as per definition, but this is history matching and this is forecasting, right? In a way, but currently it's regression. People still call it, forecasting in their papers and all. That's not correct, right? So actual forecasting is a time series problem. This is not a time series problem, right? And if you want to go ahead and still experiment with this model, make it better as a part of your research, maybe in final year or any research project, you can do a lot of things. You can resample this daily data into, monthly data. That will reduce the amount of noise you have in this data. You can see the actual trend is this. This is the decline. If you want to perform decline curve analysis, this is the data you want to perform it on. But there's a lot of noise, right? You can see it goes to zero all of a sudden. There might be shut-ins also, which is, a lot of noise that you cannot, remove, because that tells a lot about the operations of the field. But as a data scientist, you have to do something about it. So how about you resample it into monthly data? That is basically you average the data into monthly data, and then you repeat the entire process with less amount of noise. And then you observe what is the gap between the black line and the green line. And I'm sure you will find that the gap has reduced. Okay. So that's a home task that you guys can do. And I guess I would leave this understanding and this session up to this point. I have not talked about deep learning because it's not at all this particular skeleton. Everything is like 80% of the things are same. The math part, the hidden math is different. The algorithm is different. So basically you need to understand the use case that you're working on, the data that you're working on, decide what data is relevant to what kind of problem statement, what algorithm is good for what kind of problem statement. And the only difference will be at this part, okay, where you are importing the model. There you will import a artificial neural network, or maybe an LSTM model, or maybe any other kind of model. So that will keep on changing, right? New algorithms will keep on coming, and you will have to keep on training yourself on other algorithms. But the major importance is to understand the philosophy behind machine learning, and whether you understand the drawbacks of various models. So right now I'm telling you that if you want to do a deep learning project, you have to make sure you have good amount of data. Okay. So once you have millions of rows of data, high computational power, now you can use Google Colab. But if you have time, you have a lot of research done, then you can go for deep learning as well, right? So that's about it. I guess we are almost there. We have 5 minutes remaining. Let's take any questions if there are. I'm done.
Okay, thank you, sir, for the great session. We'll wait for some questions, and if there is no question, we'll end the session, okay?
Sure.
Sir, someone is asking, what is the difference between interpolation and prediction?
Okay, so interpolation is basically, suppose I give you a sequential data, right? I give you 5, 10, then the next part of the data is missing, and the next part is 20, right? Now you know the answer, what's missing, right? You know it's 15. The reason you know that is because your brain has done something like the sequential mapping, the way the sequence is working. There's a difference of 5 and stuff like that. So this is interpolation. You are trying to figure out the missing data based on the other parts of the data, the behavior of the data. But prediction I guess you are asking regarding machine learning. It's basically you are trying to figure out a model. You are trying to figure out a mapping between X and Y. You are trying to look at unseen parts of the world based on the seen parts of the world. When I say world, I mean data. You are trying to figure out a model that can talk about unseen data and find out your Y for the unseen data. Given that you have X and Y for the seen data, right? So the difference is it's kind of very obvious that interpolation is just filling in the gaps between the data, but prediction is very different. Okay.
Okay, thank you for the explanation. We have another question, which is it important to normalize the data while doing a decline curve analysis?
Yeah, so you have to look at, so if this is the data I am doing a DCA on, so you can see I have a lot of noise in this data. So I can do normalization that will help me eliminate a lot of noise. But you are talking about normalizing and not resampling. So if you want to eliminate noise, then resampling is the option. Normalizing is basically taking this entire data into a different range. That still might be noise in its own scale, but it won't help you much. It will help you train the model faster, because smaller the data magnitudes, better and quicker the machine learning is, right? But if your aim is to remove noise in the data, then normalizing is not the best solution. Resampling, moving average and stuff like that, they help you, remove noise in time series data. And because you talked about DCA, which is basically time series. So you have to look at the data. If your data is very clean and smooth, no normalizing, no resampling, nothing. You just go and do DCA. If your data looks like this, you have it.
Okay, thank you. So we are at the end of our session. Thank you for participating in our event. I'm sure that you have learned a lot about the different technologies used in the oil and gas industry. Thanks also to our instructors for their time and efforts to make our event success. And as a kind reminder, make sure to do the final quiz when it's available, and stay updated in our group to know about your certificates. Thank you.
Thank you, everyone. Have a good day. Keep practicing. Good luck.
Thank you, sir.